constructing a confidence interval for a population mean. And we've already taken a look at proportions for confidence intervals, the z-intervals. And so what we're going to talk about today is really pretty similar. A lot of the steps you're going to take when we're looking at sample means will be pretty much the same as sample proportions. So we still have a four-step process to constructing a confidence interval, to identify the parameter of interest in context, to name the procedure and show that the conditions are met, to calculate the confidence interval, and then to interpret the interval in context. The differences will be in really step 2 and step 3. In the procedure and the conditions that need to be met, and the calculation will be slightly different. So here are the conditions for inference about a population mean. We still need a random sample, so data are collected from a random sample or a randomized experiment. We still need independence, which is our 10% condition. So as long as you are sampling without replacement, the population capital N has to be greater than or equal to 10 times the sample size, lowercase n. And the third condition is normality. And so the observations need to meet one of these three things. We're no longer checking NP and N1 minus P greater than or equal to 10 because that was for proportions and we don't have P in this case. So there's three things that could satisfy the normal condition. Number one, the population could be stated to be normally distributed. Number two, the sample size should be at least 30, and then the CLT can be referenced as saying we have approximate normality. Or you can take a look at your sample data if the sample size is smaller than 30. So take a look at a normal probability plot and look for a linear trend, or look at a box plot and show that it is approximately symmetric with no strong outliers. So as long as one of those conditions is met, we have normality. Now, to be able to use the normal curve for these types of things, for sample means or population means, we need to know the value of sigma, the population standard deviation. And that's really rare. So in most cases what we use is something else. When the standard deviation of a statistic is unknown, we use the standard error to estimate it. The standard error is the sample standard deviation over the square root of n. So the only time we're able to use the normal distribution in z star and the z-curve is if we know what sigma is, but this is extremely rare. So if we don't know sigma, then we use the sample standard deviation s, but this results in a different distribution that's a little bit wider than the normal distribution, and it depends on the degrees of freedom, which are n minus 1. And this distribution is called student's t distribution. It's really similar in a lot of ways. It's symmetric and single peaked. It looks like a bell curve, kind of like a normal curve does, but it's a little bit wider. As the sample size and degrees of freedom increase, then the curve gets closer and closer to normal, but it's not exactly the same thing as the normal curve. So when we're looking at a confidence interval for population mean, we're going to be looking at, in this case, a one sample t interval. It's a one sample because we're going to be estimating with one mean, and a t interval because we won't know sigma and so we can't use the normal curve. So the confidence interval is x bar plus or minus t star times s over the square root of n. So here's the first example. Let's say that we have a random sample of 11 students taken from a large school, and what we're trying to do is estimate the weight of their backpacks. So here are the 11 pieces of sample data, the 11 weights calculated from the sample of 11. And what we want to do is construct a 95% confidence interval to estimate the true mean backpack weight for the students at this school. So this is going to be a four-step process. So step 1 is we need to explain the parameter of interest and show that in context. What will we estimate? So that's step 1. We will estimate the true mean backpack weight at this school. Step 2 is to name the procedure that we're going to run and show that the conditions for that are met. So our procedure is called a one sample t interval. So we will construct a one sample t interval at the 95% level. Our conditions for that need to be met. We need a simple random sample, and it's stated in the problem that it was a random sample of students. We need independence, so we have to show, in this case, let's assume we're sampling without replacement, that the population is sufficiently large. So since there are 11 in the sample, there need to be at least 110 students at this school. We're going to assume that it's a fairly large school and that there are more than 110 students at that school. Last thing we need is the normality condition, and this is the one that's very different from proportions. We have sample data, and we want to show that it's following an approximately normal curve. So if you enter that data into a calculator or something, or take a look at a box plot, what you get is a box plot that looks kind of like this. Let's get a scale on there. So there's 10 over here, 15, 20, let's over here 25. So here's the box plot for our data set. What we're looking for is symmetry and lack of outliers. So this doesn't appear to be very skewed. It doesn't have any outliers. It's roughly symmetric. So that should satisfy our normality condition. Now we also can look at a graph that is specifically made to assess normality, the normal probability plot. So on the Inspire, just control menu on there, change it to a normal probability plot, and sketch out what that is. So there's just a rough sketch of what the normal probability plot looks like. What we're looking for here is an approximately linear pattern, and that's what we see, and that shows that there aren't really major deviations from normality. In this step, you have to make sure that if you are referring to graphs, that you actually do sketch them. So we can say that the normality condition is approximately met. Now in step 3, we're going to go ahead and calculate our confidence interval. So that's going to be x bar plus or minus t star. Since we don't know what the population standard deviation sigma is, we have to use s. We're going to be using t star. So that's our confidence interval formula. So let's go ahead and find all those sample statistics. So x bar, if you put this into a list and spreadsheet and find your one variable statistics, x bar is 19.18 pounds. Standard deviation is 4.75 pounds. Our degrees of freedom, since we have a sample size of 11, we have 10 degrees of freedom. And t star, we need to be able to find that. There's a couple ways to do that. There's a way on the Inspire. The most straightforward way is to use this table C. I know it's kind of hard to see, but along the bottom, we're familiar with the confidence level being along the bottom. And along the left side, it lists down the degrees of freedom. So we have 10 degrees of freedom, so you're going to find that on the left side. We have a 95% confidence level, you're going to find that at the bottom. And then just follow those up until they meet. So 2.228 is the value on that table. So go ahead and write that down there. So our confidence interval is going to go from 19.18 plus or minus 2.228 times 4.75 over the square root of 10. And if you calculate that out, what you get is 19.18 plus or minus 3.19 pounds. That's going to give us a confidence interval that goes from 15.99 to 22.37 pounds. Last step is to interpret that in context, so we are 95% confident. We are 95% confident that the true mean value is between 15.99 and 22.37 pounds. Take a look at one more quick example here, and this time we won't have a set of data, but we'll have the summary statistics. So Oscar Martinez, an accountant at Dunder Mifflin, has been tasked with estimating the true mean monetary value of all the clients for their branch. He takes a random sample of 30 clients out of over 600 and finds a sample mean of $14,000 and a standard deviation of $9,600. What we want to do is construct a 90% confidence interval to estimate the true mean value. So step 1 is explain the problem, what the parameter is we're trying to find or estimate. So there we go. We will estimate the true mean monetary value for the clients at this branch. What we're going to do is construct a one sample t interval at the 90% level. Let's just make sure our conditions are met there. We need an SRS. It's stated in the problem as being an SRS. Might as well mark down that it's stated as such. We need independence, so we need the population to be sufficiently large. So the population has to be more than, they took a sample of 30, so it has to be more than 300. And we were told in the problem that the population is more than 600, so that's met. The normality condition, we're not able to take a look at a graph, so we need to show this in another way. If we were given information about a graph or told that a graph shows no skewness or anything, then we could state that as our reason. But in this case, what we have is a sample size that is large enough to use central limit theorem. So essentially, we can state that the distribution of x bar should be approximately normal because n is at least 30, and that is according to the CLT. So all of our conditions here are met. So step 3, let's go ahead and calculate that confidence interval. We have x bar plus or minus t star, and we're using t star here because we don't know sigma. We're estimating it with the sample standard deviation. So if you look in the problem, it says that he takes a sample and he finds that standard deviation, which means it's a sample standard deviation. So over times s over square root of n. So our sample statistics that we got are that x bar was 14,000, that s was 9.6 thousand. Our degrees of freedom, our sample size was 30, so we have 29 degrees of freedom. And then t star, let's go ahead and look that up in the table. Well, if you take a look at our confidence level of 90 and our degrees of freedom are 29, follow that up, 1.699. So our confidence interval is 14 plus or minus 1.699 times 9.6 over the square root of 30. If you go ahead and calculate that through, what you get is 14 plus or minus, what do we got here? 2.98. Which means our confidence interval is going to go from 11.02 to 16.98. So last thing is let's interpret what that interval means. We are 90% confident. We are 90% confident that the true mean value is between 11.02 and 16.98 thousand.